Hello? Oh my goodness.
So today.
Oh, that's good. All right.
That time.
So now I do have a thing where it can
it's recording.
pause and record. All right. All right. Should be good. So number 5, 6, 7, and 8. This all has to do with lead and orange juice. Let's first talk about a liter. A liter is a measure of what?
Volume.
Volume. How do we explain volume?
Amount of space an object takes up.
Amount of space it takes up. Good. So let's say we have 1 liter of what was it? Lead. Yeah. I thought it said lava.
Lava.
So we have 1 liter of molten lead. 1 liter. We're going to draw the same amount.
Quickly.
Yeah. It takes up a certain amount of space too. This is OJ.
OJ.
This is also 1 liter. So how does the amount of space they take up compare, Anna?
Same.
It's the same. So your answer to number 5 is C the same. Now is where it gets a little trickier. A liter of molten lead has blank a liter of orange juice. More than, less than, or the same as. Let's think about this. There's a thing called density, right? Density is an amount of, what is density?
Like how compact it is.
Sure, I like that. How compact it is, maybe. How much mass there is in a certain amount of volume, right? So, which one has more? This is the same amount of volume between these two, right? Which one's going to have more mass?
Lead.
Lead does. Let's represent that by lots of dots, okay?
More compact.
Yeah.
Dot it up.
Dot it up. Okay.
And
That's pretty good. Orange juice has...
5.
You didn't make it orange. That's a reasonable thing about it.
That's a really good call. Of course, the lead isn't.
Okay, that's not necessary.
Oh, I have to. Makes it nice and pretty. Okay,
It's full.
There you go.
good enough?
Yes.
These dots, let's say a dot represents a certain amount of mass, okay? Done already?
Yeah.
Okay. Each dot represents a certain amount of mass. So what do you notice about amounts of mass on this one?
A lot.
There's more. Okay, it's more compact, more dense. So that answers our first two. A liter of molten lead, right here. How does it compare to the mass of a liter of OJ? This has more. This is where it gets a lot more tricky. A kilogram of molten lead has more or less or same as a kilogram of orange juice. Okay, so we are comparing a kilogram. A kilogram,
Unit of weight.
close.
Mass.
Unit of mass.
Well, you look stupid.
Mass is the, how would we describe mass?
Amount of stuff.
Amount of stuff
You said stupid.
in an object.
In and out.
Okay. Amount of stuff in the object.
That's a
In number 7, it's asking about if you have a kilogram and a kilogram. So what can we say if kilogram is a unit of mass? What can we say about 1 kilogram of lead versus 1 kilogram of OJ?
It's the same.
It's the same amount.
It'd be a lot bigger thing. OJ.
Yes, it would. And here's why.
Simpson.
A lot of people don't understand how this works though. So we're going to draw this out. We have lead and OJ, but they have the same amount of mass. Now let's say this mass is represented by, say, 20 dots. Okay. Let's start out with this guy. So this has 20 dots of OJ in it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. There are 20 dots, each representing the amount of mass. So if we're saying that there is 20 dots of mass representing 1 kilogram, how many dots are we going to have here, Laura? 20. But what do we know about how closely they are packed, Caleb?
Yeah.
You're even going by Caleb now.
In fact,
You just responded to Caleb.
well, I wasn't responding. I was just kind of interrupting.
Oh, that's better. What is it?
Closer together.
They're closer together. So we are going to have these 20 dots that are closer together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17, 18, 19, and 20. Since these 20 are closer together, we can see that, hey, it takes up less space to have the same amount of volume. How about that? Did I do that right? That doesn't look very good.
Well, lead is a very soft metal, so it deforms quite easily.
It's actually very good.
It's very
Okay.
soft, though.
So you're going to have a smaller volume versus OJ. Right. I'm going to pause and see if we need to do anything else. Right. A clothesline is under tension. So it's showing like that. It's under tension when you hang from it. Why is the tension greater when the clothesline is strung horizontally than, say, if the clothesline just hung vertically? Let's say 1,000 newtons are pulling down on this. How much tension is on this string?
You counted off one on this, but you didn't mark anything. I don't really know what it is.
Okay, well, if we go through it, maybe you'll know. And hey, maybe I missed something and you can get your points back. 1,000 newtons down. How much tension is in there, Laura? 1,000 up. There's 1,000 newtons that are applied to me and thus are on the string. So on this, keep in mind each of these strings splits half of the upward force, okay? So if this is 1,000, what's this going to be for this string? It's going to be 500. And this one's 500. Okay. So 500 and 500. Why is the tension greater when the clothesline is strung horizontally? I know we don't have to do numbers necessarily, but it's easier to see it this way. What did you guys say?
Said there's no force balancing out the force of downward gravity when the string is horizontal. Which is true.
Right.
Like in a bridge, there is no force going up to balance the gravity, which is why.
Well, if the object is staying steady, then there is a force pushing up, counteracting gravity. Otherwise, if there wasn't, the gravity would pull you down. It's just that they're on a bridge. I'll get to your question. In order to have this 500 newtons upward, what has to happen also?
It's to counteract it.
Yeah, that's the whole point of having this upward. But in order to have this upward, if you're pulling at an angle like this, what are you having to pull in order to get that upward force? Sideways, a lot. You have to pull a lot sideways.
This just says plane horizontal and plane vertical. It doesn't talk anything about doing anything at an angle sideways.
Okay. Now, if you pull it all on, if you put any weight at all, it's going to be at an angle to some degree. What's that?
It doesn't say that. It's just like it makes it sound like
Yeah.
there's a clothesline like this and there's a clothesline like this. It's like chilling in the air.
And that's a bit, I'm gonna pause it and see. Let's talk about Jack and Jill then.
You are recording this, right?
Yep.
Awesome.
So Jack and Jill, make sure I am. Okay, stop or pause. Yes, we are recording. Jack and Jill are on a date. Jill is not impressed because his car breaks down and they are forced to push the car. So here's our car, right? First I asked you if they push 600 to 500 this way, right? What would be the total force? Yep, 1,100 newtons this way. You pretty much got all that right? All of you got that right. When they're in the same direction, what do? Add. Opposite, you subtract. All right, so you add or subtract depending on which direction they are. If they're not the exact opposite or same direction, what do? You break it down into forces. So that's the situation we have in this B part. If Jack pushes down with 600 newtons at 30 degrees, right? That's 30 degrees, yeah. 600 newtons at 30 degrees. Jill pushes with 500 newtons straight. And what forces affect a car? Only forward or backward, right?
Yes.
So this forward one is what's going to be important. And so we want to add to this one. This one is a funky angle, so we're going to use SOHCAHTOA, right? We can break this down into different components. Again, they're same, add. If they're opposite, subtract. If they're neither, if they're at a weird angle, break one of them down so you can add or subtract. So you get it into these components. Sideways into the car, or the forward and backward. Now the sideways force. If I push sideways into a car, what's true? It's going nowhere. I mean, it's pushing a car sideways isn't going to do any good. So this force is just going to be counteracted. It's actually going to be counteracted by the friction. If you really want to know where it goes, friction pushes back. Friction of the tires on the road. So that cancels out.
If you put enough force on it, you can't cancel out.
It's true. Yep. If you put enough force, if you're strong enough, you could overcome. That would make your arrow stronger or whatever, and it would overcome the friction, and then you would have a net force
More magnitude.
of pushing
Yeah, but-
forward.
There's a
If
demon
like
in this
a
country.
car,
if you
Okay. So we have, now we're after, again, we want to get this so that they can be added together. So all we have to do is find this guy right here. How would we do that?
Cosine.
Yep. We're breaking this down into its parts. So, and this is the 30 degree. This is just copying this angle over here. So this is 600. Since this side is adjacent to the angle, we're going to use that. So we can say cosine of 30 equals the adjacent, right, divided by the hypotenuse, which is 600 newtons. Then all we have to do, we want to get the unknown by itself. So this is 6. So to do that, we do the opposite operation. So those cancel out. 600 newtons times cosine of 30 equals A. So what is A?
519.6.
All right. 519.6 newtons. In which direction?
Forward.
Forward. All right. So guess what? We have Jill's forward force right here, or 500 newtons. And now Jack's force up here, 519.6 newtons. They can be added together to make a total of 1,019.6 newtons. Ish.
I don't know, like,
Let's say Jack is pushing. Let's do another example. We said if they're in the same direction, you would add them. Well, let's have this scenario. The car is here. Jack pushes with 700 at 20-degree angle. But Jill's kind of angry now.
So she stopped.
And she doesn't just stop. She's being obstinately opposing him, okay?
Obstacle.
So she is going to push against where he's pushing with 500 newtons of force. How would you?
She is mad.
She is mad. How would you figure? I think I can let you figure that out. So, okay, so our whole. Sorry, I'm going to say that again. Since Jill's force is forward and it's actually backward, we need to find one that's either the same or opposite direction, and that's this one. So since we know the angle here, we can say, all right, since this side is adjacent to this angle that we know, we can use the SOHCAHTOA function that uses adjacent, which is cosine. Cosine of the angle equals the adjacent, so ka, divided by the hypotenuse. So in that case, that's 700 newtons. So since our angle is 20 degrees, that means cosine of 20 equals the adjacent angle, this guy we're looking for, divided by 700. So again, we're going to multiply by 700 newtons. We can cross those guys out. So we have 700 times the cosine of 20 should equal A. So what is A?
A is
657.8-ish. All right, so that means Jack's sideways force is 657.8 newtons. And Jill's went opposite, so what are we going to do?
Subtract.
You subtract.
157.
157.
So we don't have a test till Friday now?
I won't be
No,
here
you-
Friday.
We're having it Thursday.
Oh.
Huh?
This one's what we did in the notes. The 18 is what we did in the notes.
Wait, we have
No,
tests
I'm just
tomorrow?
gonna be
Yes.
Well, I
Yeah,
know
that's
why.
what I said we were gonna
Why are
do.
a lot of people skipping class?
I don't know.
Why
I
did
think
they?
just have.
Really?
I have stuff to do with
July.
Tara.
So we're
How
not
are we able to
reading
skip
this